We present a novel shape-from template approach on monocular video that uses only vision cues from images and a mesh inextensibility regularization to prevent unrealistic stretching. Shape-from template, or SFT for short, reconstructs the 3D geometry of an object from RGB images when a template mesh and texture is known. The objective is to recover shapes that align with the input frames. This is particularly challenging for non-rigid motion, such as cloth deformation. Traditional methods rely on keypoint matching between the RGB image and the template texture. From these correspondences, a warp is estimated and the deformation can be solved in closed form. Such methods achieve real-time performance, but they can struggle when correspondences are noisy. State-of-the-art methods impose differentiable simulation and optimize physical parameters so that the rendered shapes match the image cues. While these physics-based methods can produce high-quality reconstructions, running a simulator is time-consuming. Recent advances in surrogate neural simulators accelerate runtime, but reconstructions remain limited by the physical priors within the network and can over-smooth the surfaces. In this work, we would like to reconstruct high-quality shapes as quickly as possible without using keypoint correspondences and simulation. We propose to model the deformation by a neural network f theta. Then, we leverage differentiable rendering to optimize the deformation network. At each time step t, we use the RGB image with its gradient and the object's silhouette to compute the vision losses. An exponential weighting factor is applied to focus more on color discrepancies over shading variations, which helps to recover high-frequency wrinkles. A mesh inextensibility loss is used to ensure the shapes to be physically plausible. To reconstruct from a monocular video, we employ a frame-wise optimization strategy. We seek the parameter theta t star for frame t, then pass it into frame t plus 1 as an initialization. This scheme preserves temporal coherence between frames and is the key to our significant speedup, especially for long video sequences. To evaluate our method, we compute on Phi SFT real dataset chamfer distance between the predicted shapes and the ground truth point clouds. We significantly outperform the physics-based approaches. For each video sequence, reconstruction is done in about 2 to 3 minutes, comparable to PGSFT and much faster than Phi SFT, which requires 16 to 24 hours. Our method captures fine wrinkle and high curvature details effectively. Phi SFT could reconstruct some folds while PGSFT tends to over-smooth the surfaces. In self-occlusion cases such as sequence R6, our reconstructed shape align more closely with the ground truth. We made some ablation studies for our methods. First, we run the experiments that remove image gradient, silhouette, or adaptive data loss, and compare with our default setting. Although the image gradient and silhouette loss can improve quality, the results may look similar. Our proposed exponential weighting factor on vision losses enhances significantly the performance. We can see that without the adaptive data loss, the depth map deviates substantially from the ground truth. Then, we also validate the usage of the deformation network. Predicting vertex displacements directly leads to artifacts. Adding bending energy smooths the surface but still gives high error in the depth map. In contrast, the deformation network naturally produces smooth, high-quality shapes, avoiding the need to balance a bending term against the vision losses. Finally, we test different MLP architectures of the deformation network. The larger network generally gives better performance due to their greater parameterization capacity. However, the improvement is visually minor. On the other hand, using smaller networks can struggle when dealing with more complex deformation scenarios. We can see that the number of parameters in the small MLP is not enough to capture high-frequency wrinkles as the default in the large network. Thank you for watching.